Okay, so we're going to be looking at the homework for session 6. One of the things we want to point out is that I'm probably going to break this one into a couple of separate videos because I know it's a little bit long and it may go on for a while. Okay, so you have to kind of stop, get up, come back to it later, those sorts of things. Sorry to make that loud noise. I dropped a pen on my laptop. Okay, so let's look here at each individual section. So we're supposed to do a few things here. We're supposed to write the model and the concept. So what structure do we have? That's the model. And the concept, is the operation that we think is happening here. We want to explain why we chose what we did, okay? And we want to write the solution here. So, and it's possible we may have to do more than one calculation. So let's look at A. We have a box of candy, has 2 layers, each with 8 rows and 6 columns of candy. How much candy is in the box? Okay, so this should have been an array for multiplication. So array is the structure, multiplication is the concept or the operation. Why did I choose that? I'm dealing with rows and columns, right? I have 8 rows and then 6 columns. I'm dealing with an 8 by 6 scenario, which would be 48 pieces of candy or 48 units. If we had 8 rows of candy and then we had 6 columns, we would have 48 individuals. If you think about a piece of graph paper, if you went 8 blocks high and 6 blocks across and then enclosed that into a rectangle, you would include 48 blocks. Okay. So Janet has 6 1/3 more yards of ribbon than Mike, who has 8 3/4 yards of ribbon. How many yards does Janet have? Okay, so what's going on here? If we have, Janet has 6 more yards than Mike, okay, we're trying to combine or join Janet's yards with Mike's yards because she has this much more than this. So this is a join or a union. Okay, and of course this is an addition model. Now, why did we choose it? We are combining 2 quantities. We're combining Janet's yards, sorry, not units, Janet's yards plus Mike's yards. Okay, we wanted to calculate this. We've got 6 1/3 and 8 3/4. Automatically, most of us are used to dealing with common denominators. So we're looking at essentially 6 4/12 and 8 9/12. We combine those, we end up with 14 13/12, which would be 15 1/12. Okay. I kept my whole numbers separate to the end, added them, then added the fractions. You have more than one whole, so added that on, and then I have a 12 left over. Okay, moving on. A man bought 50 feet of wallpaper border. He cuts off 10 feet, 6 3/8 inches for one wall, and 3 feet, 2 7/8 inches for a second wall. What is the total length of wallpaper border that's left? Okay, so this is takeaway. And obviously it's a model for subtraction. Now, why did we choose that? Because we start with a specific amount of something, and then we are removing it, actually taking away twice here. We're taking away for the first wall and then the second wall, and it wants to know what is left. Okay, so we start out with 50 feet. For me, if I'm dealing with different measurements, I always try to start out with common units. It's a little bit easier to do that. So I'm going to turn this into inches when I think about feet, just so that will be a little bit easier to work with. Okay, so if I have 50 feet at 12 feet each, that's 600 inches of wallpaper border. Okay, and the first time I cut it, I'm going to take off 10 feet 6 3/8 inches. Okay, so that 10 feet, that's 120 inches, plus the 6 inches, plus the 3/8. So for that first wall, I'm really removing 126 3/8 of an inch. Okay, for wall number 1. 126 3/8. I know that looks like 4 inches. Okay, so this is wall 1. Then I'm going to remove that. So it's pretty easy to take care of the 126. Okay, we're at 600. We remove 100. We have 500 left. Then we remove 26. Okay, we would have 474 inches after we remove that other 26. And then we have to remove 3/8 of an inch. Okay, so at that moment, I have 473 inches and 5/8 of an inch. Okay, if you're thinking through that, you could do that with a calculator as well. At this point, our focus is not necessarily on the math, it is on the models. Okay, so this is what's left after wall 1. So now we go to wall 2. So we have this 473 5/8 of an inch, and we're going to remove 3 feet, 2 7/8 of an inch for wall 2. Okay, so that 3 feet, that's going to be 36 inches. And then we're also removing another 2 7/8. So for this second wall, we are removing 38 7/8 of an inch. Okay, so let's think about what we've got here. We have 473 5/8. Start with the holes first. If we have 473 and I need to remove 30, 30 would put me at 443. And then I need to remove another 8. Okay, so I would be at 435 at that point. So I've taken all of the 38. Now I need to remove 7/8 of an inch. Well, I have 5/8. There's that fraction part. So that gives me 5. So I need another 2/8 of an inch from a hole. Okay, so that's going to give me 434 6/8, or if you simplify it, 434 3/4 of an inch left in this situation. Okay, so again, we could, at this point, we could very easily calculate those with technology. As we get later on in the semester, though, we would not want to do that. Okay, so why did I know it's take away? Again, I'm starting with an amount and I am removing it. So I'm going to clear up some space here so I can move down to D. In 2013, the total U.S. national debt is about 16 trillion. Okay, so pretty large. If there are 316 million people in the United States, how much does each person owe on the national debt? Okay, so this is a sharing for division model. Sorry, just have clicked off of what we were going for. In terms of a sharing for division model, this is the partitive. Basically, why we chose this, we have a big debt and we're going to share it equally among a bunch of people. Okay, so hopefully we would know that this is going to be a smaller amount. Okay, if we have people to share it amongst. So let's kind of envision what that's going to be. Okay, so we have this large debt, so it's 16 trillion. And we want to share it among 316 million people. Okay, now we've got to be able to write those numbers out, or at least envision them in terms of scientific notation. So if we're at 16 trillion, let's think what that would look like. Okay, so if so far, this would be hundreds, 100,000s. This right now is 16 million, so it doesn't work for us. Okay, so we need another set of zeros that would make this should be millions. So here we have 16 billion. That's still not enough. So now we've got $16 trillion. Yes, so hundreds, 100,000s, 100 millions, 100 billions, and this would be 100 trillions. But we don't have 100 trillions. We just have 16 trillion. And we're going to share that among 316 million people. Okay. Here we would have just hundreds. Here we would have 100,000, so that's not enough. So there we have 316 million people. Now at this point, you would either want to bring in a calculator so that you could simply calculate that. You could also represent scientific notation. That would be possible. But either way, I'm just going to look and see what our final answer should be. I'm going to type mine into my calculator. So I have 1, 2, 3, 4, 12 zeros. Okay. And I'm going to divide by 316 and 6 zeros. And that gives me a share of about $50,632.91. Okay, so that's about what each person would owe if we were going to pay for the national debt. That probably scares us a little. Okay, so let's move on to E. At a height of 29,035 feet, okay, that's the highest mountain in the world. It's Mount Everest in the Himalayas, and the highest mountain in the U.S. is Mount McKinley. How much higher is Mount Everest than Mount McKinley? Okay, so here we have two quantities or two measurements. In this case, it's the height of a mountain, and we're wanting to find out the difference between them. So this is a comparison. Okay, and again, that is a subtraction question. We're looking for the difference when we compare things. So we should be pretty used to relating subtraction to the word difference. Okay, so we know Mount Everest is taller. We know it's a bigger number. It's the tallest mountain. And we want to subtract the shorter mountain to find out the difference between them. Okay, so about 8,000 feet in the difference. Let's go on to F. We have 4 swimmers compete in the last heat of the 400-meter crawl. They are equally matched, and it is unclear who will win. The red and blue ribbons given to the 2 winners. How many different ways could the ribbons be awarded? Okay. This is obviously a combination. We're looking for the different groups or how we could this could result, and that is a multiplication model. Okay, now how would we answer that? We've got 4 swimmers. Okay, we could think about first place, okay, as swimmer 1, 2, 3, or 4. And then second place, depending on who was chosen, okay, if swimmer 1 got first place, then we would have an option of 2, 3, or 4 for second. Here we would have an option of 1, 3, or 4 for second, 1, 2, or 4 for second, and 1, 2, or 3 for second. Okay, why did we have to adjust? Because if the swimmer 1 got first place, he can't also, or she also can't get second. Okay, so it says who will win red and blue, okay, to 2 winners. How many different ways could the ribbons be awarded? Oh, okay. Yeah, so we are looking for first and second place. I was thinking there for a second that we were looking for 2 winners. That might be a little bit different. So here, look what we've got. Look at the possible combinations. We've got here, this would be swimmer 1 gets first, and then swimmer 2 gets second. This would be swimmer 1 gets first and 3 gets second. Same thing for 4 here. So these are 3 outcomes. Here, swimmer 2 gets first and 1 gets second. 2 gets first and 3 gets second. 2 gets first and 4 gets second. So here's another 3 possible combinations. This would be swimmer 3's in first and then 1's in second. And another 3 combinations. And again, the last three combinations, assuming that swimmer 4 gets first place. Okay. So all in all here, we have 12 combinations. Now, why is it 12 and not 16? Because most people want to say 4 choices, 2 choices, or two selections of 4 choices. That has to be 16. Well, that's not necessarily true here, because if we're talking about a competition, we assume that one individual can't hold 2 places at the same time. So we do have 4 choices for first place. But no matter who wins first, we're only going to have 3 resulting choices for second place. So that makes 12 different combinations we could get there. Okay. Charles left a dozen very large cookies in the teacher's lounge. Everyone who saw them thought one cookie was too large to eat and only took a third of a cookie. How many teachers did Charles feed? Okay. So we're looking at this. This is a division problem, clearly, but this is repeated subtraction. If you have trouble viewing this, think about what would actually happen. Every teacher would walk into the lounge and they would subtract 1/3 of a cookie from his collection. Okay, so this is division, repeated subtraction. I know how much I have to share. I know how much each person is getting. What I don't know is how many people I can share with. Okay, so here I know what I'm giving to each person. I just don't know how many people are going to get it. Okay, that is the repeated subtraction model. Okay, so we start with a dozen, and we want to know how many people can get a third of a cookie from that dozen. Okay, we could do the math here, but honestly, this should be a pretty easy thing to figure out. If you think about one cookie, you think about a large chocolate chip cookie, and it can be shared among 3 people. So 1 person, 2 people, 3 people get 1 cookie. If you have 12 of those, you should be able to feed 36 people. Okay. Moving on to H. Susan's scores on each hole of golf tournament were 2 below par, 3 above, 1 below, blah, 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 blah. How far apart or below par was Susan at the end of 18 holes of golf? Okay, so this is still a join model, and it is an addition situation. The only thing here, instead of just using natural numbers, here we're introducing integers. Okay, when we hear 2 below, 3 above, 1 below, if you've ever kept golf score before, 2 below would be like -2. Okay, 3 above would be +3. Okay, so we would be joining, we would be looking at the overall union of these scores. Okay, so what exactly would we be joining or adding? Well, we have to consider, okay, then below and above as negative and positive. So below, we would start with -2. They would add 3. Then we would subtract 1 because it's below 1. Par just means break even, so 0. 2 below par, okay, that's going to be a subtraction of 2. 1 above par plus 1. 3 below par would be -3. 3 below would be -3. 1 below would be -1. 1 above would be +1. Par, that would be 0, 0. Okay. 4 above would be +4. 2 above would be +2. 3 below would be -3. 1 below would be -1. And 1 below, which would be -1. I think there's also a par in there, which is just +0. Okay, should be altogether -6. Okay, at the end, we get a result of -6 when we join all this. So what would this mean? She would be 6 below par. Okay, keep trucking. We're almost done with these. Okay, the last bit of laundry detergent in the bottle came to only 1/6 of a cup. How much must be added to have the half cup required for a load of laundry? Okay, so this is a situation where we're starting with an amount of detergent. So we know we have 1/6. We're going to add something to it, and then we're going to get a half a cup. Okay, this is the missing addend. We're missing something we're going to add. So how are we going to do that? We are going to subtract that from a half. So basically, I want to know what I need to add to a sixth to make a half. That should be a pretty simple thing to do, because how would you get 1/6 to be 1/2? You'd have to have 3/6, right, to equal a half. So I have 1. I'd need 2 more. So you may represent it as 1/3. You could see how you might do that. Altogether, that would be a half, because I would have 2/6 here with this 1/3, 1/6 here with what I started with, and together that would make a half a cup of detergent. According to U.S. industry estimates, 56 billion aluminum cans were recycled in 2010. How many aluminum cans are recycled every day? Okay, so we're starting out with this huge number of cans, 56 billion, and we're going to literally share that among every day. We want to see how that distributes to every day in a year. So that is the sharing model of division. Okay, we are starting out with all of these sharing of all these cans. Okay, so 56 billion. Let's see if we can write it. That would be 56,000. That doesn't work. That would be 56 million. That doesn't work. There we go. 56 billion. Okay, hundreds, 100,000s, 100 millions. And up here we would have 100 billions if we had that many, but we don't. And we traditionally think that there are 365 days in every year. Okay, so if I wanted to calculate this, I might use my calculator, or I might use some scientific notation strategies. I knew those. So get somewhere around, it's a lot. Let's see here. Let me write the number out. So it's about 153,424,657.5 cans a day. Okay. We'll stop when we get to I here, and then we'll move on to the second question in a second video. So according to the state law, the amount of radon released from waste at any location cannot exceed this as a working level. A study of 2 different locations report this as the working level and this at the second location. By how much do these meet or not meet the state standard? Okay, so here we're actually comparing 2 different quantities. Okay, this is the state standard. This is what the state says is allowed. Okay, that's the level you're allowed. Now we've got location 1 and we have location 2. So let's separate them. This is what it has to be. Let's see what they are. So location 1 is 0.043. Okay, if you compare that to the standard, okay, location 1 exceeds the standards because it's more than. Okay, if you were to compare these, 0.043, that should be, this is what we know this is tenths, hundredths, thousandths. So this is 43 1,000ths, whereas this is 33 1,000ths. So location 1 is too much. It's too much. It exceeds. Okay. How much? It is 10 1,000ths in excess. It's over by 10 1,000ths. Okay. So let's look at location 2. Oh, did I just do that backwards? I did. No, well, that's all right. It's easy to fix. We'll call this location 2. Come over here and look at location 1. Okay, So that was location 2. Here we go. We've got 0.0095. So let's compare that to the standard. Okay. This is 95/10,000ths. Okay. Whereas here we still have 33,000ths. If we were to expand this to 10,000ths, just so we could make it equivalent, we would have just so we could make it as a part of the same whole, we would have 333. So it's easier to see that the standard is higher. So location 1 does not exceed. It is within the limits for what's been given here as in terms of parts. So location 2 exceeded by 10 1,000ths, whereas location 1 is well below. Okay, here we had 33,000ths. You haven't even gotten up to 10,000ths yet. Okay, so that is our rationale there. So question I, which is the last scenario, the star Deneb is approximately 1.5 times 10 to the 19 meters from Earth. So long way, right? Like if we were to write this number out, we would have 1, 5, and then 18 zeros. A light year, the distance that light travels in 1 year, is about 9.46 times 10 to the 15 meters. What's the distance from Earth to Deneb measured in light years? Okay, so what do we have here? We have this big distance, and we're wanting to know how many light years is in that big distance. Okay, well, every time we measure a light year, we would be taking a chunk of that away. So this is a repeated subtraction for division. Okay, we have this huge distance, so we have the total distance. And we're going to divide that by the distance for 1 light year. Okay, every time I can take away one of these amounts from this overall distance, I have another light year. I've made another complete light year. Now, in terms of how to do that division, make this a lot easier on ourselves if we wanted to. So we have 9.46 times 10 to the 15th. We can mark out common factors. 10 to the 15th is in common. So all I have up here left is 10 to the 14th. Okay, so I have essentially 15,000. That's 1 times 10 to the 4th divided by 9.46. It's a little bit easier to do. Okay, nonetheless, even if you used a calculator, whatever method you chose here, when you do this calculation, you should come up with about 1,585.62 light years that you should be able to get out of that total distance. Okay. So if you have particular questions about this, you may want to join me for office hours. You may want to talk about it tomorrow. For right now, I don't want you to freak out too much about the inability or ability to do the specific calculation, but can you pick out the structure that is shown here and what concept or what operation it's modeling? That's what's specifically important at this time.